Okay, good morning, everyone. I hope you haven't grown tired of me yet. It's the third time, fourth time I'm here. This is actually why I came for here. So we have heard quite a bit about FRB hosts already. I'm going to assure you I'm not going to bother you more with FRB hosts. I'm going to cover all the rest. So I hope to give you some overview of what we know and all the things that we don't know about the host galaxies of, let's say, the most extreme transients. Because if I go to all kinds of transients, I'm going to be still here next week. Okay, so our big challenge is when we observe host galaxies and, well, any kind of transients, but especially host galaxies, is that, if you look at GRBs span everything up to redshifts of almost 10. With supernova, it's a bit less bad, but they have supernova that redshift almost 4. So we always struggle between the sensitivity that we can reach with our instruments. Of course, that has been improving with time, but you see here curves of different limiting magnitudes, and you very quickly run into problems actually detecting your host, or even if you do spectroscopy, those limits go down. You have to more look at the lowest limit. Or the problem of resolution. So anything ground-based, seeing limited, you're about here. So as soon as you go out to a bit of redshift, you're in the order of kiloparsecs, only that it can reserve. And of course, the redshift problem is that our lines that we use very quickly go into the infrared, so we have to use not just ground-based stuff. Well, you can still do ground-based stuff, but infrared gets complicated. Okay, so I'm starting with long GRB hosts. Well, we thought for a long time that long GRB hosts are about this size. If you see this nice compilation here, there are actually different ones. With this one of the famous examples that I'm going to speak in a bit. So at the beginning, I'm going down a bit the memory lane when we were all still young and pretty. At least me. Probably some of you were still in high school. That's very depressing. So we have detected host galaxies of gamma ray bursts almost since the beginning. So in 1997, this was actually the first host galaxy ever detected of a long GRB. And quickly after came one of the famous 1880425. And of course, early on, people tried to do samples and see, can we say anything from the host galaxy on the progenitor of these things. This was back then when there was some supernova detected coincident with our GRB, but we didn't know yet even that long GRBs were connected to Broad 1C supernovae. And so this is a mass meteoricity relation from Savali et al. Very early on. It looks still very rough. So you see that GRB hosts, long GRB hosts, are metal poor and have low masses, but it was not that clear yet what was going on here. One of the first samples, Christina et al. 2004, saw that they have on average high star formation rates. We have rather high specific star formation rates. That's a paper based stellar masses from K-band, from Spitzer. And there's probably so they had a constant kind of specific star formation rate, probably only because we are missing higher mass gamma ray burst hosts. I think I'm actually going to go down and follow that Sandra doesn't get nervous that I'm falling. I guess it's actually better when I'm an angle here, because otherwise I go crazy. Okay, so what was also done very early on is try to get HST data to see how the hosts, well, first of all, how they look like, and second, where the actual GRB is located. And so we found that, for example, a lot of GRB hosts are actually rather compact, and that the GRB is located within the R50 radius of the host, so that's actually rather close to the center. And how are gamma ray burst locations correlated with the blue light of the host? And there is some sample here already from 2007, where it became clear that long GRBs sites are probably the most correlated to blue light in the host, while core collapse supernovae are much closer to the average distribution, which is also not entirely true, as we're going to see a little bit later. Then we had some early larger samples. This was the first attempt for an unbiased sample, the tough sample that was done at dark while I was doing my PhD. Try to just select the hosts that have been observed by SWIFT, not very extinguished by galactic extinction, where we have actually good localizations. They were able to fill this, what we had in the beginning between redshift 1 and 2, we have the so-called redshift desert, because it's difficult to detect, well, you do get absorption line redshifts, but not always. Sometimes we didn't have a host yet, and at redshift 1 or 2, you already have to go to the infrared in order to detect emission lines. So you did that with X-shooter, and suddenly this gap here started to fill in. So there is actually a lot of gamma ray bursts around the maximum stuff of well, cosmic star formation history. Another result was that only 1/3 were Lyman alpha emitters, possibly due to low dust, and that the UV luminosity function is consistent with gamma ray burst selecting galaxies according to star formation, especially at low redshift. But they are kind of underluminous at high redshift, although I think that it was back then an observational bias, because as soon as we go up to redshift beyond 4 or 5, it gets very interesting. There's a lot of James Webb data of galaxies out at that redshift trying to determine the luminosity function and the global star formation rate. And some of them disagree a lot. With GRBs, we can in principle do that, but our sample is still, unfortunately, very, very small. And the next sample that's much larger and with a much bigger data set, basically a follow-up of the very early Castro-Thöne et al. Paper that is done, obtained a lot of time with Spitzer to observe more than 100 host galaxies. I think now with the extended shows, it's more than 100 host galaxies. And we have been involved with GTC to do a lot of follow-up in other bands. There's spectroscopy. Well, of course, there's a lot of literature data. And so we see that there is some increase in the mass and the absolute magnitude of the host galaxies with redshift, but there are very few massive hosts at low redshift. So it's not that here, if that would be, I mean, of course, we can only probe the more massive hosts at higher redshift, but at lower redshift, they are absent. So these lines should, because at low redshift, you would detect them all, and we don't. So there seems to be something going on, possibly because they avoid massive galaxies at low redshift because those are the ones that are more metal rich. So that's an indication that they are selecting galaxies by the metallicity. And they all have very high star formation rates. This is something that's, well, basically an ongoing study, partially done by Feli in his PhD thesis last year. If you look at gamma ray burst hosts, these were masses and star formation rates obtained by SED fitting, very broadband SED fitting, including the Spitzer data, of course, of the host. They tended to have lower star formation rates versus mass before a shoal sample, and this whole sample went up, considering a lot more hosts. So you have to be careful if you start to do something which it's something that the FRB hosts are experiencing right now. They still have low number statistics. First, things can be all over the place. Then they might shift to one direction. Then you have another sample, and you might shift in another direction again. So you have to be very careful in what you're doing. And small samples are always a bad idea, but sometimes it's the only thing you can do. Then we started to also obtain some spectral samples, especially with X-shooter, because X-shooter goes all the way to the infrared, so we can cover a much broader wavelength range. We see here again that star formation rates in GRB hosts on average increase with redshift and the mass, what I already had before. And one interesting thing is that we found with the X-shooter sample is the star formation rate correlates with the width of the line. So maybe that's just bigger hosts, maybe that is more turbulent hosts, maybe that is hosts with outflows. I'm going to come back to that in a second. And one thing that we are still a bit puzzled about is that there There are a few, very few, but they do exist, supermetallicity host galaxies. And we're still not sure what's actually going on. Is there, I mean, this, for example, is resolved. Is there some star-forming region that is actually metal poor? That's where the GRB was. Is this like a sideline effect that we don't see the actual GRB region behind? It's not clear. Food for study. And so what we can do for, unfortunately, only very few cases is, I mean, all this, what I showed you before, were data of the entire global host galaxy, either the spectrum or the SED, and taking the photometry of the entire galaxy. And what we want to do, especially in those cases, those few cases that I showed in the very beginning, that we have larger host galaxies, to actually see how are the conditions at the actual GRB site. It depends very much on what kind of galaxy you have. I've been here on Monday talking about a supernova host where we could also have resolved data, resolved spectroscopy. But if you take a global spectrum of the entire host galaxy, it would be rather close actually to the star-forming region, just because that star-forming region where the GRB, in that case the supernova, was, is basically dominating the light, because this is so highly star-forming and so luminous that whatever you get in the spectrum, 80% of that is from that region. But that's not always the case. This is, for example, the case here in 100316D, one of these more typical GRB dwarf galaxies, one of the lowest redshift hosts we actually have. It was close to a very massive star-forming region, which happens in many cases. Also this one, our famous 1998 BW, was close to actually a very massive star-forming region that's so young that it shows Wolf-Rayet features. It was actually on top of another star-forming region, but not the most extreme part, not the most extreme region of the host. And I put these two apart, which is, well, two of the other long GRB hosts where we have resolved spectroscopy, because they are unfortunately a bit special. So both of them are what we first called supernova less long gamma reburst. So we haven't detected a broadband 1C supernova in them. This one is a very nearby galaxy. It's still a bit unclear what's going on, but it seems to be something, if that's really in that galaxy, that would be very close to the center in a rather dusty and very high metallicity region. This is a famous 060505, which was located in a region that would have been perfectly fine with being a long GRB, standard long GRB site, because it's metal poor, highly star-forming. But there are maybe some indications that this was also associated with a kilonova, so that it was actually not coming from a massive star, but from a merger. So as I said, low sample statistics is very bad, so we are trying to improve on this, not just with GRB hosts, but also with other ones, but that's what we have so far. I just very quickly want to mention about kinematics, also to show the few other GRB hosts where we have IFU spectra. So there was in Lunan mentioned yesterday in her talk that they detect some outflow in magnesium. In this case, I think it was in the supernova and not in the host spectrum. And so we might see something similar in gamma ray burst hosts. This is the only sample that we have of high spectral resolution and high spatial resolution gamma ray burst host galaxies, taken with flames, which otherwise is unfortunately a dreadful spectrograph, and it doesn't exist anymore. There's decommission, probably for a reason. But you can actually do line profiles, which is something that you cannot do very often. And so we saw that all GRB hosts have if you look at the prominent emission lines, you have an error component, which is the main bulk of the gas, and you have some broad components. All of them had that. And it actually, the broad component and the maximum velocity correlates with the star formation. So there is some indication that there's actually quite some outflows going on, probably from the intense star formation that we have in those galaxies. Okay, and I'm not going to say much about this. We can also observe GRB hosts in radio. We can determine the gas mass, the molecular gas fraction, which is higher than for average galaxies. We can do some H1 maps, which you see the resolution is not very good, but they are usually not, they don't look like your nice H1 disks that you see for your standard nearby star-forming galaxy. And you can also do some resolved maps in CO with ALMA nowadays. But that's, I mean, the resolution here is unfortunately still bad. And I want to show you this nice example of one of the closest gamma ray burst hosts that we could study in across the entire wavelength. So you see here visible and UV in CO, actually a resolved map, the only proper resolved map that we have, and in H1. Also here we have some funny 2 H1 lobes, has nothing to do with your normal nice H1 disk. And so this is a spiral galaxy, a bit smaller than the Milky Way, but of that ballpark. And the GRB is in a metal poor region in the outskirts of that galaxy. So you see that galaxy has some star formation going on in a ring that's a bit closer to the center than the GRB is. Less star formation in the center. And the GRB region is one of the youngest regions in that host. There's 2 other ones here which have basically completely absence of an old stellar population. But if you compare that to other GRB hosts and locations, so this is a GRB site. The green ones are global spectra of other GRB hosts. Well, the ionization and metallicity is not as extreme as we would have expected. That GRB, although, has been a low luminosity GRB, so maybe there is some connection between metallicity and the luminosity of the GRB. And you can do this as high redshift. We have already seen a poster today on this. So there are 2 hosts that have been here resolved with a program from Pat Shady. As probably some of you know, Pat Shady unfortunately passed away early this year. So I wanted to highlight her talk a bit because I think she has been one of the important people in the field. And so she managed in the very early phase of James Webb to get observations of the first high redshift resolved GRB hosts. And those are 2 examples from her student. So you see that this is not some easy galaxy. There's actually several knots here. There might be interacting systems. And in this case, for example, the absorption and emission metallicity, which also heard already in a poster before, matches very well. In this case, not, although the metallicity is only an upper limit because there was no nitrogen detected. So you see the picture gets even more complicated, higher redshift. Of course, we need more data on that as well. And well, see actually if there is some kind of evolution also in the result stuff. And just a quick word on that, you can also study GRB hosts in absorption. I'm not going, this is my only slide on this, just to prepare for the next slide. To determine whether there's, well, at low redshift, you have to do the absorption, the emission line metallicity is high redshift, you do absorption line metallicities, which is actually a different thing. So you have to detect Lyman alpha in absorption and some metal lines, and then comparing that to the solar abundance, you can determine a metallicity. You can sometimes even do dust depletion resolved. And this was so these are how the spectra look like. We determine things. This is actually a very curious sightline, which, so if you usually see your Balmer lines in emission, in this case, this is a GRB afterglow spectrum. You see them in absorption because it's probably a very dense region. And so Pat exactly was trying to see whether you can reconcile the absorption and emission line metallicities. And the short answer is yes, you can, but it depends very much on which metallicity calibrator you're using. If you use some other calibrator, it's a lot of thing about ionization, how those ionization fields are at high redshift and things like that. Your match is actually not that great. And so there was another poster also by Anne Inkenhag today that the TE metallicities, which are directly from measuring the 4363 line and the strong line calibrators, at least match in one case. But yes, I agree with her. We should give more data to that, if anyone is in a James Webb panel. Let me see. So the second thing I'm going to talk about of extreme hosts of extreme supernovae are, of course, superluminous supernovae. As the name says, they're superluminous. So they are extreme supernovae. Maybe their hosts are also extreme. So about 10 years ago, we started to compile the first sample on different superluminous supernova hosts. And so what we saw is that superluminous, so there are two types. There's superluminous supernova type 1, which don't have hydrogen in their spectra, and type 2, which do have hydrogen in their spectra. A lot of the type 2 are actually type 2n supernovae. I'm going to mostly be talking about superluminous supernova type 1, because in the beginning we thought maybe they would be similar to GRBs. They are actually not. They are more extreme. So they have lower metallicities, which you also see in the mass metallicity diagram. They have lower masses, and they have, for example, very strong oxygen 3 emission, which tells that this is a very galaxy with a very high ionization field. And of course, also very high star formation rate. In specific star formation rate, 50% of them are actually extreme emission line galaxies. And yeah, superluminous 1 and 2 clearly have different hosts. The supernovae of type 1 clearly select their galaxy also according to star formation and especially to metallicity. So they really seem to not occur at high metallicities. But they also don't really agree with any other sample. They look more like ELGs, but they're also not all of them, so they're more of a mixed bag. So we cannot really see they match exactly this and that sample. And also here there have been some nice studies with HST data about their location and how well they're correlated with the blue light and the offset. They are even closer towards the center of the host than GRBs. But they're slightly less concentrated in the brightest regions, although possibly here there's quite a lot of error. And so what's happening with redshift? There is also this sample here where you see the specific star formation in different redshift bins. You see that with redshift it gets to, well, the masses maybe don't change too much, but it gets to more extreme specific star formation rates. And you have a bit of, well, we do have a bit of evolution in the star formation rate and in the mass. And there's a few very high redshift for supernova studies. Not so high for if you do GRBs, but there are quite a few now that are trying to detect at redshift larger than 1.5. So as I said in the beginning, the highest has like redshift 3.8 at the moment. There have not been any host studies on this yet. Okay, on just very quickly on that, we have very few cases on where we actually resolve the superluminous supernova with an IFU. This one was very interesting because this was actually a metal-rich galaxy. So we thought, oh, what about the metal pore cutoff? And if you look closer, the GRB was actually in a, well, still not metal pore region, but we studied the stellar population and we found out that there's an underlying metal pore stellar population, which probably gave rise to the superluminous supernova. So our theory is still fine. And this is not really resolved. This is not an IFU spectrum. This is just a long slit of a very extreme, one of these extreme emission line galaxy hosts. Okay. And in the end, I'm going to talk only a few minutes because I'm running out of time on general supernova hosts. So, well, first of all, I wanted to show a picture of my cat. So these are my 5 beautiful cats. So, well, the thing is, if you look at more things, sometimes they look similar, sometimes they look obviously different, but sometimes even if you look closer, it's like, what is what? If we look at a specific environment, can we say this has to be the environment of a supernova type X or not? And I think the only time, I mean, we can see trends. We have been seeing trends. We have seen that in the superluminous supernova and GRBs and FRBs compared to that, for example. There are some indications, but even sometimes if you look close enough, from which cat is one or the other, what we actually have to see, what we would like to see in the end, in where we can say, okay, this thing had this and that property, is if we either deduct properties from the explosion, or we can pinpoint the progenitor star. Then you know who is who. Okay. So while supernova hosts have been studied since much longer than the other samples, because we have been observing supernovae already centuries ago. This was the first extragalactic supernova actually detected in the 19th century. Very nice. But the only supernova that we have seen in Andromeda since, in real time, of course, the supernova remnants. Well, some other, like the famous 1987A. So what have we seen from, of course, there's samples of core collapse supernovae that are not superluminous or GRB are much larger, although if you go to broadline 1Cs and 1B and 1Cs, your samples get much smaller. And it seems that even core collapse supernova select the host due to star formation, and broadline 1Cs avoid high mass galaxies. So broadline 1Cs, which are kind of GRBs that didn't have a jet, although sometimes we don't know. And let's get to this. So there is one, there's some famous compilation, actually both papers by Mariam Mojas et al., trying to see whether there's differences between supernova 1C, broadline 1C, 1B, and GRBs. In the beginning, it was a complete mess. So it was not clear whether there was actually any difference. If you take larger samples, you start to see that, well, that 1C hosts, not broadline, 1C hosts are more metal-rich and have higher masses than the rest. And broadline 1C host environments and GRBs are kind of similar. There's much bigger samples on that. Although, as I said, if you go to the 1Cs and broadline 1Cs, you get very few. And it also becomes less clear. There's actually in the, so the supernova 1C on younger regions with more massive stars. But is there a metallicity difference between the 1C, 1B, and type 2? That's also not clear. But we know that there have to be differences even within a galaxy, because there are galaxies where we have observed several supernova. The record is NGC 6946 with 9 or 10 supernova. And our famous example here, NGC 2770, which probably a lot of you know, is 2008D that had a shock breakout, which just got in fashion again with the shock breakouts. And that actually had 3 different supernova types, 21B, 21B, 11C. Yes, 21B, 11C, 2008D, and a type 2N. But we need, well, people to work on this. Resolution is important, as I said, depends on if you have where your actual supernova is located, whether that has a uniform property or not. I'm not saying anything about F-hosts, and I leave you with the future of host studies. Of course, we need bigger glasses. Things are going to be, the samples of hosts are going to grow a lot now with all the surveys. We don't have to go and apply for observing time to observe every single host of a transient that we find. A lot of them are going to come automatically in those surveys, at least down to a certain magnitude. We are still going to need big glasses and deep observations for the more faint ones, also in space. And I said, absolutely, what we would like to observe in the end is actually the progenitor, which we're never going to be able to do more than in our local universe, but we can try. Thank you.
Thank you. Questions for Christina? We have time for a few. Yes.
Thank you for the talk. I have something, well, my question is slightly tangential. So you, there were 2 long GLB hosts before. On the slide before, you had the really good spatial and spectral resolution observations, like the slide 1 before that. You said there were like 2 events where you were like, oh, these are really interesting host galaxies, but it doesn't look like they're like traditional long GRBs because maybe they didn't have supernovae. Could you just could you explain to me like what it was that was like, oh, there's no supernova there? Was it like spectral observations? Like, yeah,
Which ones?
yeah.
Yes.
I'm sorry, that's like why it's not totally relevant.
So that was already back in 2006 that we did follow up the afterglow, and that was low redshift. So we should have easily detected a supernova. Of course, if you go to redshift, whatever, 0.8 or 1, it gets a bit more tricky. You might have dust extinction, you don't see it. But in that case, it was, I mean, you see it's a resolved galaxy. It was redshift 0.09. So if there is a supernova, it would have to have been extremely faint, like it was, and would be unreasonable. So I probably did not have a supernova. There are teams afterwards that claim that there might be kilonova emission.
Okay, thank you. And Sandra? Yeah.
You mentioned earlier a galaxy GRB host, which have two components in the mission lines, narrow and the broad, right? So can you show a little better? So the narrow and broad component are the same redshift, first question. And the
Yes.
second, how large, what is sigma for both components? Just to understand how large they are, the both components. In kilometers, yeah, in kilometers per second.
So you see here, this is the full width of maximum of the broad component in kilometers per second.
How much?
That's 100, 150, 200.
Yeah, so they're narrow. I mean, even the broad is narrow, correct?
Well, the broad is up to the highest one is 250 kilometers per second.
So there is no AGN possible contamination there.
No, none of these hosts have any AGN. That was ruled out long ago. Yeah.
Okay, thank you. We need to move to the next talk. Let's thank Christina again. Yeah. Sorry. So we move to our final host galaxy talk of the morning by Valentina, who will tell us about what high redshift gamma ray bursts and low redshift metal poor galaxies have in common. Please go ahead.
Thank you so much. Hi everyone, I'm Valentina. I work at Observatoire Paris with Susanna Bergani and her group. And today I will show you, I will talk about a project we have in which we are comparing some properties of GRB host galaxies with metal poor galaxies that are in the local universe using a multi-wavelength spectroscopy. So just to introduce you with a concept of multi-phase gas that I will be talking about all the talk. Nearby the star-forming regions, we have very massive stars that ionize the gas around. So we have very elements on very high ionized states nearby those regions. But farther away, we have colder neutral gas where we have lower ionized species. Both are very important to understand the bulk of metals, and metals are very important because they transport momentum, they cool the gas, so they have a fundamental role in star formation and feedback and regulation. And we also can have a complex kinematics structure in this gas. So we analyze optical rest frame through emission lines, and the neutral gas will be studied through ultraviolet spectroscopy, where we will have different absorption features and of different elements, and these absorption features can be very complex and give us also the kinematic structure of the neutral gas. So we are, for the first sample, we are interested in long gamma rays, specifically the afterglow emission of the relativistic jet when enters into interaction with the ISM. It glows, it's very bright. So we have a source of light that will pass through the neutral gas and will give us this beautiful spectra where we can see a Lyman forest absorptions of all the intervening system between the observed galaxy and the observer. And also these galaxies, GRB host galaxies, have normally very high column densities of neutral hydrogen. So we have DLAs profiles, and we have a bunch of metals, metal absorption profiles. For this sample, we have 45 GRBs observed with X-shooter in all the arms, UV, optical, and infrared, near-infrared, and UV spectral data. The column densities, so all the metallicities here for the GRB sample are based on absorption line analysis. So the comparison sample is composed of some blue dwarf galaxies in the local universe. These are analogs of high redshift galaxies in terms of masses. They are very low mass. They have low metallicities, very high star forming rates, and they have very high ionized parameters. So they are nearby, and they allow high resolution imaging and spectroscopic studies. And it's very important to remind that the bulk of baryonic mass is in the neutral phase. So it's very, very important to have both the neutral and ionized phase metallicities and kinematics. So here I show you just, I just rescaled the redshift of the local sample that is very local, is from redshift 0 to 0.12, and the GRB sample expands into redshift 1 and 6. And this is just to show you a comparison of the neutral hydrogen column densities. So we are mostly sampling in both samples very high column densities of the neutral hydrogen. So these are very rich gas galaxies. The local galaxy sample, the data comes from COS, that is the Cosmic Original Spectrograph on board of Hubble. And we have 45 nearby galaxies, from which we have 31 showing these DLAs profiles. So we have comparable neutral hydrogen column densities. So comparing also the metallicity to mass ratio, we have here the distribution of the local galaxies that spans from very low mass galaxies to 10 to the 10 solar masses. The difficulty for the GRBs is just, you see here, most of these points are upper limits. It's very difficult for high redshift host galaxies to determine the stellar masses. So we have mostly photometry from Spitzer, infrared photometry. So we have upper limits. Okay, so now that we have comparable samples, we extract from literature, and we also measure some of the column densities for some elements that we can compare in both samples. Here I selected iron and sulfur. So I just show the relation between sulfur and iron abundances for both samples. They span more or less the same parameter space. But we see from the distribution that in average, the GRB sample are a little bit less metal rich than the local galaxies. And we also applied a Pearson correlation analysis to see how correlated are the abundances. So we see that when we have higher iron abundances, we have also higher sulfur abundances. The same exercise for silicon. And the fact that we have less or lower metallicities for the GRB sample could be due to the fact that for higher redshift galaxies, we have probably dustier environments, so we could have dust depletion. This is under investigation currently. So we are just trying to apply an analysis of dust depletion. That's the next step. Okay, so regarding kinematics, we we use the same strategy as Su et al. 2025 for the local galaxy sample. So they have both optical spectroscopy and ultraviolet spectroscopy. For the optical spectroscopy, they can derive the systematic redshift, and as a reference, this will be the redshift of the ISM. On this, they applied a multi-component emission line fitting and absorption line fitting also for the for different species in the ultraviolet. So they can measure blue shifted components that will give us the magnitude of outflows in those systems. So they found for the local galaxies that there are higher velocities from absorption lines. So we recover blue shifted components that are at higher velocities in the neutral phase. So here I just showed you an example following the same strategy for this GRB 150915A. So we have oxygen 3 and H alpha. So we have oxygen 3 here in this case is the strongest line. So we define the systematic velocity, and with reference of this velocity, we also applied multi-component Gaussian profiles for the emission lines and void profiles for the absorption lines. So we have different components, and we see that the blue shifted components for both low ionized ions and high ionized ions in the neutral phase expand more to the blue shifted part. So we have a stronger, more rapid outflows in the ultraviolet. So also for the emission lines, it's very difficult to have a good signal to noise just to determine the structure, the velocity structure of the kinematics. So we have only 6 GRBs for which we have both the ionized gas flow outflow velocities and the neutral gas outflow velocities. And we find that higher average outflow velocities from absorption lines versus emission lines, which is in agreement with what was found for the local galaxy sample, although we have much lower velocities in the ionized gas for our sample. And in the sample, we also try to compare in the neutral gas phase if the agreement of the velocities that we measure from low ionized species and high ionized species, we have a very good agreement, except for a pair of outliers. That is also in agreement with the studies on the local high redshift analogs. Okay, so I just led you here with summary, but the important take-off message is that we compared 2 samples, one of GRB host galaxies and one of local high redshift analogs that are used as laboratories to understand the high redshift universe in this JWST era, in which we need to enlarge the statistics to understand metallicity, kinematics, and other parameters for high redshift systems. Thank you so much.
Thank you. Questions? Yes, up there.
Thank you, very interesting. Can you comment, and sorry if I missed this, and if this is too technical, I'm happy to discuss later, but can you comment on how did the iron abundance derivation for the Galaxies sample? How was the iron abundance for the Galaxies sample derived?
This is for the Galaxies sample? Okay.
And is this taken from the literature, or did you do this yourself?
Yes, the literature, but it was a study here from James, and I was the second author. We measured these iron metallicities with absorption lines in the UV from COST data. They are from the neutral phase.
Okay, I'm happy. I would be interested to discuss more.
Yeah, sure.
Yeah, I'm also very interested actually to see these absorption line studies, and it would be interesting to see where your GRB galaxies compare to the superluminous host galaxies, where we did a similar study actually with
Yes,
using both emission and absorption
with the
lines.
starch to
Yeah.
other comparison samples.
Yeah,
Sure,
yeah. But I think we need to move to the next speaker. So let's thank the speaker again. Now we switch topics a little bit from host galaxies back to supernovae. So the first speaker will be Wynn, who will tell us about flash spectroscopy.
Good. Sweet. Okay. Morning, everyone. Thanks for sticking it out on your half day. So I'm Wynn. I'm a NASA Hubble Fellow at Caltech. And I wanted to come and share some recent observations of young supernovae in the ultraviolet, and also try to get people excited about the ultraviolet and the future prospects of UV spectroscopy in future space missions. So why do we care about the ultraviolet? Well, we may have all different reasons behind why the ultraviolet is interesting to us, but for supernovae in particular, if flux was converted into information, the ultraviolet would hold the majority of the flux relative to the optical for a young supernova continuum here. So, we are only sampling typically with our optical spectra less than 10% of the overall flux of young supernovae. If emission and absorption lines were information, we would definitely be missing the majority of the information, because there's orders of magnitude more transitions of primordial elements, as well as just the elements of the inner ejecta and circumstellar environment in the ultraviolet that we cannot access and understand the full chemical picture of supernovae without UV spectroscopy. We're kind of gaining some traction in understanding that the ultraviolet emission of objects like core-collapsed supernovae from red supergiants that either slam into circumstellar material or don't slam into circumstellar material are quite diverse in the ultraviolet. So these are all supernovae from red supergiants, and they can have orders of magnitudes different luminosities at early times in their ultraviolet, given the proximity of circumstellar material, so gas that was lost in the final years to decades before explosion, and that can lead to a completely different ultraviolet signature at early times if we have early enough UV light curves. So in red are CSM interacting, in black are not. In terms of objects that are just kind of more bare red supergiants, are typical type 2Ps without a lot of circumstellar material. Those red supergiants that were not so, incorrectly behaved before explosion and erupting a lot of material, the ultraviolet is still a promising place to look for transitions of primordial iron group elements like aluminum, chromium, magnesium, titanium, etc., that also form from the outer layers of the fast-moving hot supernova ejecta. And so to truly understand the chemical abundance of supernova ejecta at early times, we also really need the ultraviolet, even though there's a lot of blanketing effects and metallicity effects as well, because we really just don't understand. And also just to show the difference between an object with a lot of circumstellar interaction and a red supergiant exploding into a relatively clean environment. The difference is pretty stark. So just even having a supernova spectrum to confirm that difference is really imperative. Supernova UV spectroscopy has been relatively limited, especially at early times. Still to date, the earliest UV spectra ever obtained of any supernova is 1987A. And after that is 1993J. And then only recently, really in the last 5-10 years, have we started to have programs that utilize the HST capabilities to try to get on target of a young supernova in the ultraviolet within days of explosion. It's extremely difficult process because it requires so much scheduling for HST to turn around and undo a schedule and do an ultra rapid disruptive TOO. So we really only get approximately one far UV or near UV supernova spectra per year, and we've been kind of incrementally moving at that rate. because only one ultra-rapid TOO is awarded every year. So in the last, I guess, 5 years, we've had 3 published type 2 supernovae observed in the ultraviolet at early times. And so you really see how fast things turn around. So the rising light curve of supernova, you have to, discover it, announce the detection, then trigger, get the HST trigger, confirm spectroscopically, and you can get a very beautiful spectral sequence like this. We've done this in 2023. We've done it in 2022. There's a couple other that are unpublished now, but this is a slow rate if we're trying to understand the UV diversity of type 2 supernovae or supernovae in general at early times. So to try to kind of address this disparity in the community, we utilize this new initiative at Space Telescope called Flexible Thursdays. Flexible Thursdays was introduced a couple cycles back, and it provided the time domain community and really just anyone in the astronomical community an opportunity to trigger HST and a limited number of instruments on HST one Thursday per month and observe something on a Thursday every month. TBD, like whether that's the first Thursday or the third Thursday, but just one time a year, so 12 opportunities, 24 total triggers. This was an initiative that then we took advantage of in cycles 31 and 32 to obtain UV spectroscopy of type 2 supernovae. So we felt that we could probably utilize at least one Thursday a month to obtain 1 to 2 UV spectra with the STIS CCD. It's not the best UV instrument on HST. It only provides near UV coverage, but it is our opportunity to try to obtain young, early UV spectra of type 2 supernovae. So I'm going to walk through that process, but I'll highlight, the problems just already with HST. It's aging, it's moving into modes that are more safe for it, and as a result, the effective sky area has been cut approximately 50% in just the last couple of years because of the gyro, the move to single gyro mode. So how did Flexible Thursdays work for us in terms of trying to actually provide a young supernova candidate for HST to observe on a given Thursday? So if I want to do this, then the following Thursday, if I want supernovae observed within a week of explosion, I need to be discovering a new supernova, fresh, between the previous Thursday and Sunday, and Sunday before the trigger. Because on Monday night at 2 a.m. Pacific, I have to submit my request. It then goes through processing. I approve it Tuesday morning. It then goes through 48 hours of scheduling. And then by Thursday, I can then observe it. So I need then a targeted strategy. And thankfully, we have a very nice dedicated transient discovery method with ZTF, where we, on that given weekend before Flexible Thursday trigger, we had ZTF only hit HST visible fields, so we knew that any transient discovered in those fields would have HST visibility. Like I said, HST has limited visibility now, so we really need to be efficient about where we point and try to discover supernovae. I can't just trigger HST on any supernova that's discovered on the weekend before, because HST might not have visibility. So where we put our efforts is really key. So this is just a nice example of a use case that actually worked. So ZTF discovers this infant supernova on Thursday or Friday. It's confirmed with an ATLAS detection within 24 hours. We obtain an optical spectrum to confirm that it is a young core collapse supernova. We actually trigger SWIFT within the weekend, and SWIFT observes within 48 hours to confirm a UV luminosity. That's not required, but that's really great to calibrate our exposures with HST. And then Monday night, I provide a HST trigger, and then by Thursday we actually have one of the earliest type 2 supernova spectra at less than 5 days post-explosion with a UV component as well. So in principle, this works, and it actually yielded a nice sample of type 2 supernovae combined with the archival sample that we were steadily building up with ultra-rapid or just serendipitous observations. And so to date, this is kind of the current less than 12 to 13 days post-explosion sample of UV spectra of type 2 supernovae, both type 2Ns interacting, type 2Bs, like more hydrogen poor, as well as just normal type 2Ps. And so it's not many objects, but I think that we're actually starting to build a population of UV spectra of core collapse supernovae that then we can do for some sample statistics, or at least just motivate future missions to do this in a more routine way. So pre-2024, before we started this Flexible Thursdays initiative and had 2 cycles going to try to obtain UV spectra, There are only approximately 3 core cup supernovae with spectra at less than a week and only 6 with UV spectra at less than 2 weeks. We then increased that by more than a factor of 3, and then within 1 week and 2 weeks. And we have a number of subtypes that we explored with this program. I'm not going to talk about all of them, but if you're interested in any particular UV spectra of your favorite core collapse supernova, come chat with me, and we can look at more of the specifics. Yeah, I want to highlight some of the specific supernova cases and like the science that we've done with them, just to kind of give you an idea about what's interesting about UV spectra and what can actually be done in terms of the physics. So to start with the type 2Ps or type 2Ls or type 2 normal supernovae. So as a reminder, these are supernovae, the most common supernovae. They come from red supergiant progenitors with or without a significant amount of mass loss before explosion. And for those without a significant amount of mass loss, the UV spectra compared to also archival and literature objects remains pretty unimpressive and not too diverse, but that's good. We've confirmed that young core collapse supernovae in the ultraviolet are relatively well behaved. And there's subtleties in terms of like iron profiles and other emission lines and absorption lines that we can look at in more detail with our radiative transfer models shown in red, yellow, and blue here. But overall, we're kind of constraining the idea that type 2 supernovae are relatively similar in the ultraviolet if there's no additional energy injection from shock power. All right. But what's maybe a nice interesting thing that we can do with UV spectra in the future is if we continue to build more radiative transfer models for core collapse supernovae, compare to the UV continuum and try to infer, say, progenitor radii from UV spectra at early times. That's an interesting thing that we can do, as well as just the kinematics of the explosion, because these are material that is moving in the fastest parts of the supernova ejecta and also traces more of the ejecta given optical depth effects. One other class that I got really excited about was the type 2N. So these are objects that come from maybe unknown progenitors, but definitely massive stars that interact with a lot of circumstellar material. With this program, we were able to obtain some of the earliest type 2N UV spectra to date. And coupled with UV optical near IR, we have this really beautiful SED that can tell us about the properties of the emission lines that come from the shock power as the forward shock collides with dense circumstellar material. And what's really interesting about the UV is that UV emission lines are not all recombination. Some of them, and the majority of them, are resonance. So unlike optical and near IR recombination lines that have these electron scattering wings and come from like global electron scattering of photons in the entire ionized medium of the circumstellar gas, the UV lines actually trace further out locations of the CSM because they just keep getting absorbed. And so until I actually see a UV photon, it needs to be out in a very large radius comparative to the optical photon. So it's actually tracing larger distances and also asymmetries in the CSM. If I see really booming emission lines in the optical and my radiative transfer models would predict booming lines in the UV and I don't see them, that's telling me that there are pieces, the lines of sight, that are actually lower density in a 3D sense than a 1D radiative transfer model would tell me. And so that's interesting in terms of constraining CSM asymmetries and mass loss and things like that. Lastly, I'll just highlight type 2b. So this is a relatively hydrogen deficient core collapse supernova. And with this, we obtained some of the earliest UV spectra to date and showed also signatures of CSM interaction. And this was led by my student, Rajula Yuti, who provided this really nice multi-wavelength campaign of these. So just to summarize in a few seconds, the UV, landscape is really bright. I'm part of the UVEX team, so this is going to routinely obtain UV spectra of at least 10 to 20 core collapse supernovae in the far UV within days, if not hours of explosion. We're now automating swift triggering of spectra of early supernovae. High Z supernovae are somehow UV bright. That's really interesting. Late time supernovae are really UV bright. That's really interesting. I think the UV sky is really intriguing and that we should all be caring about it. So thank you.
Yes, we have a question over there.
You commented CSM asymmetry. Yeah, I didn't follow exactly. So could you a little bit more elaborate?
Sure.
How
Yeah.
we can explore using?
Absolutely. So The difference between the optical and the UV is really crucial here. So you have the way that these emission lines form is different. And so if I compare my UV spectrum to a radiative transfer model that's just along one line of sight, and so it's just probing CSM interaction along one sight line, then my CSM density is kind of fixed. And just you can see the model disparity between an observation in black and the emission lines that we're missing or not seeing in the observations. And that's just because you may have resonance transitions that occur at much lower optical depths at further radii. And so you need to pierce through regions along in a 2D space or a 3D space that are lower density, get to lower optical depths than in a radiative transfer model that's just along one line of sight. And you're only really seeing just the highest density, one density profile line of sight. But yeah, we can chat more about it. Yeah, also, yeah.
One final question, and then we move to the next speaker.
Thanks, Will, for the very interesting talk. One thing that I wonder is that with what you just discussed, can you make some statement on, for example, viewing angle dependence? So like assuming that the CSM is perhaps like a disk,
yeah.
Could you make some statement on whether you're perhaps facing it from the pole or the edge?
I think we can definitely do like a sweep along viewing angle. If you were to just say, yeah, like, and you could do this without full radiative transfer. You could just do this with like a cloudy simulation, just like what is the emissivity of my lines, assuming a different density profile. So do I see lines of a different ratio along different density profiles? So just build a gas and then do that. Yeah, so I think that's definitely possible. Yeah, just something we need to do.
Cool.
Yeah.
Thanks.
Okay, let's thank Wynn again. And we continue with supernovae, but we're going to move from the ultraviolet into the infrared with Kyle Medler telling us about JWST observations. Yeah. Okay, please go ahead.
Thank you. Hello, I'm Kyle. I work as a postdoc at the University of Hawaii, and today I'm going to talk about kind of progenitor structure or ejector structure and molecules that we observed in JWST observations of 3 type 2 supernovae. Let's start off with a bit of background. So we observed throughout the universe that there's significant amounts of dust within galaxies, while the local universe galaxies can easily be explained by AGB stars, which undergo significant amounts of dust formation throughout their life. The early universe galaxies are far too young for this, for AGB stars to be the dominant dust formation. And so people invoke supernovae as the main source of this early universe dust. However, dust formation in supernovae is not simple, requiring very specific range of ejector temperature and velocities in order to facilitate this dust formation. One mechanism that can be, or that occurs to get the ejector into the correct temperature and velocity range is through the formation of molecules within the ejector. So these molecules, typically those of carbon and silicon monoxide, form within the ejector and act as coolants, reducing the temperature of the ejector to below the dust condensation point, allowing for dust to actually form within the ejector itself. In addition, these molecules act as nucleation points, facilitating the formation of new dust within the ejector. However, while the properties of dust and supernovae vary quite significantly based on the progenitor masses of these objects, understanding the range of properties of molecules that form, and therefore the masses of dust that form within these supernovae, require us to look at supernovae from across multiple different mass ranges. And so my team, or the collaboration that I'm part of, have been able to obtain JWST observations of multiple different types of core collapse supernovae in order to study the formation of molecules and consequently dust forming within these objects. And I'll focus on 3 specific ones today. So what are these targets? So first off, we have the low mass explosion of 2022 ACKO. It was a explosion of a red supergiant on the lower limit of explodability for these kind of core collapse events. And it was observed through pre-explosion imaging, determined to explode in a very clean environment. Next, we have 2023 IXF, a very well-known type 2 supernovae, which exploded from a progenitor of significantly higher mass to 22 ACKO. In addition, the progenitor of IXF went through multiple epochs of significant mass loss prior to its explosion, creating a very thick CSM kind of surrounding the progenitor. And then finally, we have 24 GGI, which was kind of a more typical type 2 supernovae with only a single epoch of mass loss just prior to its explosion. So what do the different ejector structures look like for these 3 events? So from the JWST observations, we were able to look at multiple lines across the near and mid-infrared. So to start off with, we can look at the structure of the hydrogen features, kind of the classical or the most iconic kind of features of type 2s. So during the initial phase, so during the initial phase, during the photospheric phase, when hydrogen is still recombining in the ejector, we get classical P Cygni profiles in all 3 supernovae, with 22 ACKO kind of being a bit different to GGI and IXF in the sense that it's relatively narrow emission features, just due to its being a significantly lower mass explosion. Then it's not until the nebula phase where significant diversity starts to emerge between these 3 objects, with 23 IXF developing significant structure within the ejector or within the hydrogen profile associated with multiple shells of CSM interaction. GGI developing a small notch on the blue side of the feature, which is again associated with CSM interaction, although this time only a single lower density CSM. And then finally, 22 ACKO, which remained a very narrow, very kind of clean emission feature, suggesting very little to no CSM interaction. But looking deeper into the ejector through intermediate mass and ion group elements available through JWST observations, we see kind of a bit of a diversity between the 2 objects. So for 22 ACKO, we see the ion group elements and kind of outer hydrogen and helium are kind of all clustered in a very similar kind of velocity range, whereas the intermediate mass elements, which are typically more formed through the stellar burning process during the progenitor's life, are kind of more offset, suggesting a kind of diversity in the location of these elements within the ejector. For 22 or 23 IXF and 24 GGI, we kind of get a much more kind of uniform distribution of all of these elements, although there's still signs of asymmetry within these emission line profiles that we can see. So kind of combining the what we know about the hydrogen envelope along with these deeper intermediate mass and ion group elements, we kind of put together a rough structure for these kind of objects. So for 22 ACKO, we see, or we suggest that there's kind of a large diversity between the location of the intermediate mass elements and the ion group elements, which we kind of suggest could be from either a bipolar Wynn that's launched from the central compact object that forms within these events, or from a choke jet that fails to kind of breach out through the helium envelope In contrast, 23 IXF and 24 GGI kind of have a more or a less asymmetric kind of distribution of these elements, although there is still intrinsic asymmetry within the explosion itself. So from the structure, we can move on to the molecules that we observe in these objects. So for the fitting of molecules, we use this code developed by Tycho, shown up here, the molecule fitting analysis tool, which iteratively fits the emission profiles from the first overtone and fundamental emission bands of primarily carbon monoxide, but also other elements like silicon monoxide, to kind of determine the best fit temperature structure in order to fully reproduce the emission lines that we see. So what do these look like? Well, for 22 ACKO, we see we tried initially fitting the fundamental and first overtone at both epochs of our observations with a spherical kind of non-clumped emission. And we observed that while it does fit the first overtone relatively well, a non-clumped model struggles to reproduce the emission features that we see in the fundamental bands, kind of over here, especially at later times. So instead, we move to including clumping within the ejector, going for a kind of prolate kind of clumps of CO, where we found significant improvements in the shape of the fits. While we could fit the later time observations with this prolate model, because it depends heavily on the first overtone, the fundamental, which kind of sets the parameters of the ejector and the shape of the clumps, we're unable to fit the first epoch, but we can see that there's a clear large increase in the CO mass between the two epochs, even with just the smooth non-clumping emission. So for 23 IXF, this work is still ongoing. Preliminary results suggest that, as with ACKO, and as I'll soon show, we need significant amounts of clumping within the ejector, and we need a very high density profile for the molecules in order to reproduce the flux ratios that we observe between the fundamental and first overtone. So moving on to 24 GGI. Again, we initially tried with a non-clumped model, but found that in order to reproduce the flux ratios between the fundamental and first overtone, we needed a significant amount of clumping. And we see quite a large decrease in the amount of molecules over the course of about 100 days between our observations. With GGI, we were able to also fit the SIO features after the CO, using the temperature structure derived from fitting the CO first overtone and fundamental. And then, since I'm low on time, I'll show a comparison of these two objects that we've been able to fit so far. So we see in 22 ACKO an increase in CO mass over time, suggesting that we haven't reached the end of CO formation, or at least the formation formation to destruction ratio is still quite large. In comparison, we see in 24 GGI that both with the silicate monoxide and carbon monoxide, a decrease in the mass over time, which could be because in 24 GGI there's a larger amount of hard radiation kind of destroying the CO. So while there might still be CO forming within 24 GGI, it's significantly less than the rate at which CO is destroyed. So I'll leave up my summary and kind of end there.
Thank you. Questions? We have time for a few. Yes, Eddie.
Thanks, Kyle. So with the difference with the choke jet in ACKO versus the not so asymmetric explosion in IXF and GGI, do you see differences in the molecular formation that you attribute to that?
We don't see I don't think we see significant differences apart from just the raw kind of mass differences and the rate at which CO is forming over time. So I'm not sure if the formation of CO can easily distinguish between the two.
Dan, over there.
So in some supernova remnants, there are also claims of asymmetries and structures in the different elements. Is the structure you see here consistent with what has been reported in some of the galactic supernova remnants that have been observed?
I believe so. I think for kind of a choke jet kind of with the ACKO, it kind of matches the distribution we see in something like 87A and kind of other remnants. Although I haven't looked too deep into like the galactic remnants to really determine if they're very similar.
Interesting comparison.
Mm-hmm.
Okay, we need to move to the next speaker, but let's thank Kyle again. And we have one final talk for today, which is going to be Wasif Shaqil. Yes, telling us about the changing nature of WOH G64.
Perfect. So hello, everyone. I'm Wasif, and I'm a first-year PhD student. I'm working with Emma Bieser and Nathan Smith. And today I'll talk about this extreme red supergiant called WOH G64. I'll present the evolution of its spectra over the last 2 decades and discuss what we think about this star and also the implications for this object on the pre-supernova evolution of massive stars. So let me first set the stage by mentioning a bit about red supergiants and why we care about them. So massive stars between about 8 to 30 solar masses are expected to become red supergiants. And direct imaging over the last 2 decades have shown that these red supergiants are the progenitors of type 2P supernovae. Although there is some debate regarding the most massive red supergiants because we do not actually see red supergiants above red supergiant progenitors above 20 solar masses, and that is called the red supergiant problem. I'll not go into detail about it, but it's worth mentioning here. The mass loss throughout the lifetime of a massive star also significantly impacts the endpoints or the resulting type of the supernovae. So in this HR diagram, each of these tracks are different mass loss rates and different masses. And if we take the example of the 12 solar mass star and a normal mass loss rate, we expect the star to end its life at the yellow point. But if we increase the mass loss rate by a factor of 10, this is what happens, and this is where the star ends its life. We see a few blue loops, it moves around and ends its life in a much bluer region of the HR diagram. So it is important to really understand the pre-supernova evolution of massive stars, and extreme objects like WOH G64 is an excellent laboratory to just do that. So this is the most luminous red supergiant in the LMC with a luminosity corresponding to an initial mass of about 25 solar masses. It has a very extreme rate of mass loss with greater than 10 to the minus 4 solar masses per year. So this is a VLTI image of this star, and it is the only image of a star that is taken in this detail outside of our own galaxy. And you can see that there is an asymmetric torus of dust around the star, which hints that there might have been previous extreme mass loss events in the past. It is also identified as the only truly dust-enshrouded red supergiant in the LMC, and that is particularly because of this extreme extinction of 8 magnitudes. So as for the dust-enshrouded red supergiants, if you look at the mass loss rate versus the luminosity plane, for the LMC red supergiant, you see that WOH G64 is basically an outlier in the sample. So many people actually argue that all the single red supergiants go through a phase like the dust enshrouded phase, and that is a phase where they have very extreme mass loss rates. So why do we actually care about this red supergiant? So this is the spectrum of WOH G64 in 2007. It looked like a very normal red supergiant. You see the characteristic titanium oxide bands. And in the span of less than 10 years, it had gone from looking like that to looking like this. So a very drastic change. The TIO bands disappeared, and you see a lot of emission lines, including a lot of forbidden emission lines. So something really extreme must be going on with this star for the spectrum to have changed that drastically in less than 10 years. And if you look at the light curve, it has a pulsating period of about 900 days. And if you look around 2014, 2015, it brightens in the V band, the blue one here, but the same brightening is not seen in the I or the R band. That means that the star gets bluer around 2015. And this is just before the spectrum that we have in 2016, where we see that it changed drastically. So this change in the brightness could be related to the spectral change as well. We see another change, a dimming event around 2024, 25. It's a dimming event of 2 magnitudes, and we have now newer spectra from last year where we see something really interesting happen. So this is the evolution of the spectra over the last 2 decades. And in general, we can see that it's very variable, but if we look at some of the features, we see a lot of forbidden emission lines. You do not expect to see forbidden emission lines in red supergiants. You see them maybe in hotter main sequence stars or yellow supergiants, yellow hypergiants, or B bracket E stars, but not in red supergiants. And one of the main features is that the TIO bands, which I said that had disappeared in 2016, and they are not present in 2021 as well, but they have now reappeared in our last spectra from last year. That means that this star is still a red supergiant, but it clearly did not look like one in 2016 and 2021. And so something really extreme was going on there. And we now know that most massive stars are actually in binary systems. And this behavior of WOH G64 is actually hard to explain or hard to reconcile with single star models. So basically, some people argue that red supergiants can move bluewards to become post-red supergiant objects, where they have blue loops and become maybe yellow hypergiants or yellow supergiants. But this is clearly not such a transition, because the transition is like would take place in thousands or maybe more years, and this is like 5 or 10 years, and it's clearly back to being a red supergiant again. So we cannot explain the behavior of WOH G64 with single star models. And because of the composite spectral features because of the forbidden emission lines and the TIO bands, there is now a growing consensus that this is a binary system. We think the same. We think it is a periodic behavior in a very eccentric binary system. So the companion star gets close to the red supergiant atmosphere. It plunges into the RSG atmosphere and ejects the outer envelope of the red supergiant. This exposes the outer cooler layers. This exposes the inner hotter layers of the red supergiant, and the TIO bands disappear for less than 10 years. And that is because you need very cool atmospheres to form TIO molecules. And we think that it's a periodic behavior because we now see that the TIO bands are back again. And the overall spectrum is also going back to its pre-2016 phase. So the wider implications of this for pre-supernova evolution is that we now know that most red supergiant progenitors are enshrouded by very dense CSM, and that and Wynn has already talked a bit about that. We can see that from the very early spectra of type 2 supernovae, where you see very highly ionized emission lines that disappear within a few days or weeks. And that means that there is very dense circumstellar material within a very short range of the progenitor, which must have been ejected at very extreme rates a few months or a year prior to the supernova explosion. For example, the progenitor of 2023, IXF, was a very dusty, variable, and extreme mass-losing red supergiant, quite like WOH G64. And because of the asymmetry of the ejecta around the supernova or the progenitor, there is an argument that this was not a single star system, but a binary system, because you expect asymmetric ejecta or asymmetric outflows from binary interactions. And we see quite a similar thing with WOH G64. And as for the dust-enshrouded red supergiant, the only dust-enshrouded red supergiant that we know of in the LMC may not even be a single star, but maybe a binary star. That possibly means that the dust enshroudment that we see in the pre-supernova evolution is driven by binary interaction. It's not a single star phenomenon. And we also know that the single star mass loss is very weak. It is about 10 to the minus 6, 7 solar masses per year. And so if WOH G64 were to explode now, we might see something similar to an interacting supernovae. And that strengthens the argument that binary interactions play a very major role in pre-supernova evolution of massive stars, especially for the interacting supernovae case. So I'll conclude my talk here by leaving the summary, and I'm ready to take any questions. Thank you.
Thank you so much. Yes, I see we already have a question from Wynn.
Thank you, Wasif. That was a fantastic talk. This is a super cool object. Do you have predictions for the next potential eruption if this is a periodic system with a binary that is now moving towards apastron and then we'll come back through periastron again? Like, do you have a prediction for when that will happen?
So we have looked at some analytical calculation of the orbital period, and we think it's greater than 50 years. So, but we do not have a upper limit to it. It can be thousands of years because it's very eccentric.
Okay.
So it can be very long, yeah.
Okay.
Well, people think, I have a question. So like, have you looked at how this star sort of moves around in the HR diagram during this variability? And could you comment on the implications for, let's say, using, you know, photometry from HST or something to, I'm thinking back to the red supergiant problem that we're using sort of single epoch or sometimes even photometry taking at different epochs to derive these masses, which maybe is dangerous. I don't know.
Right. So we actually do not see any movement around the HR diagram. There was a paper, I think last year or the year before, which said that this has transitioned to a yellow hypergiant. But now we clearly see that it's not. So that was probably just because of this binary interaction that it looked like it was a hotter star. But we think it's the same, so around the 35,000 Kelvin mark, which is typical for a red supergiant. And as for your second question, I really do not have an answer to that. I'm sorry.
Thanks. Just a quick question about what's the potential evidence for a binary orbit? Is there a blue excess in the SED or some radial movement in the spectra?
We do have the spectra in the bluer part, but it's not really clear. And we do have some radial velocity calculations, but it's very variable, so it's really hard to get accurate measurements. But I think there's some people who are going to look at this again with the VLTI, and they are trying to find the companion. Hopefully, we'll have something in the future.
Yeah, thanks.
Okay, one final question, I think.
I guess building off that with the VLT, so what observations would you like in order to confirm whether this is a binary system or not? Like in your dream scenario?
Maybe just the observation of the companion, like clearly, like they are doing. I think the last week there was a talk on the Betelgeuse. They found the companion, something like that. Yeah.
So cool.
Big news.
I know that. Thanks.